Hello, everybody. My name is Mark Mandel. Welcome again to Code Live with Google Cloud, episode 2, season 4. I think that's right. I'm pretty sure right.
I think you were supposed to say the season first before you say episode, but
Look,
hey,
don't tell me what to do, Murphy. It's fine.
I'm
You're my
I'm
guest.
I'm saying I think I did not say you
You think?
have
Yeah, all
to.
right, fair enough. Fair enough. So I, like I said, I'm Mark. I tech lead developer relations for gaming on Google Cloud. But I have a wonderful guest host here today who has been on multiple times before. Murphy, why don't you introduce yourself for those people who have yet to meet your brilliance?
I think I have been on every single season so far.
You should
If
get like a award or
I
something.
don't know, I think like save it for season 5, but this is season 4. I think if I make once I make 5 season, I probably get a jacket.
We'll
For
give you
5
something
times.
like just totally ridiculous. Like here is a USB charger. Just
Hey,
I don't know something. I
as
don't know.
long as it's like properly branded, I'll take it. Hi, my name is Mofi. I work at Google Cloud as well as, and my focus area is mostly GKE. So this season, I'm getting to talk about things that I actually work on, which is fantastic.
Very nice, very nice. So Murphy, what are we talking about today? What exciting doohickery have you brought for us?
Well, okay. So exciting, hopefully. But what we're going to talk about is how do you go about serving really, really large models, or not? Doesn't have to be models. Something really, really, really large that does not fit in a single node anymore on Kubernetes.
Okay.
So just to paint a picture, so Kubernetes, of course, are like running things like any application that you can put in a container, and you could put a bunch of those containers together into a pod, and those pods make up deployments, and you can run multiple of the deployment of the same application. Now, until very recently, most of our application, probably the most demanding of the application, were your traditional Java application that required like, I don't know, tens of gigabytes of RAM. And at the higher, I think the biggest Java application I've seen was probably like at startup time required like 30 plus gigabytes of RAM. It was like a really big Java monolith. And that,
Hi, I run game servers, so
right. So those are probably bigger. But like, again, me personally, so game server.
right,
So
right.
give me a number. Like, what is the most memory it would need to start up?
Yeah, like that wouldn't actually be that unreasonable. 30 gig, 40 gig.
Yeah. So let's say, argument's sake, like 100 gigabytes of memory to start up, right?
Okay.
And on Google Cloud and pretty much most cloud providers, it's not super like a unique to find VMs that can hold that much space. Like I will just like look at it. So right, I'm gonna go into this cluster that I have spun up. I want to add a node pool, and I want to find big machines, right? So I want to add a node. Okay, so internet is being interesting, but okay, a node
Are
pool.
you sharing your screen? Are you meant to be sharing your screen?
I'm going to add that. Here you go.
There we
Okay.
go. That would be better. Thank you.
Yeah, that would be useful.
Perfect.
So again, it doesn't matter what I'm doing here, but I'm just like showing an example node pool that I can create in my cluster now.
Right.
Which is I could create a high memory cluster. So this
and we can make some pretty high memory clusters. Like that's a thing. We can do that.
Like again, this is a single node with 128 gigabytes of memory. So that would do it. I can go even bigger. This is our E2s. I could go to one of our like C4. They have even bigger machines. I could go like high memory. This one happens to have like about 1.5 terabyte of memory. So that would run most things.
What is that for?
I don't know who that is for.
I have some ideas on who that is for, but I don't want to say in case I'm wrong.
Again, these are C machines, so these are for like high performance computing and like really expensive like compute that you do. So again, 1.5 terabyte memory would run most things.
Right.
But now in the GPU world, you could also have like pretty chunky machines, right? You could have like this H100. Each of the GPU has 80 gigabyte of video memory. And then you have like 8 of them. So you're talking about 640 gigabyte of GPU memory. Pretty big stuff. Can run most things. Now, the thing you get into trouble with, let's say you are Meta. You release this pretty nice model, Llama 3405 billion parameter. So you just like add that into the mix. Willie, hello. You've joined us.
Willie, we are live. I'm just letting you out.
Oh, I'm sorry. No, sorry about that. Everybody,
all good.
Are you? Did you start a little bit early? Oh no, 4 minutes late. Everybody. I'm sorry about that.
Willie does all that programming and make sure that we run smoothly, and Willie is doing his job right now.
This is the beauty of live events, and I apologize. Sorry for.
No, it's all good. Again, this is proof that we do this live, and these are not at all practice. So it's all good. So you have about 640 gigabytes of video memory available in a single machine through 8 GPUs.
Cool.
But let's say Llama 3, 4, or 5 billion parameter model gets released, and you can do the math, and there are some websites that does it. But if you're talking about 405 billion parameter models in full precision, it requires about 1900 gigabytes of memory to fit the entire model into your video, like GPU.
Okay, and that's video memory. That's not necessarily like RAM
that's
memory.
Not RAM. That's like GPU memory. Now,
cool.
The full model in full precision. Most people would not run that model in full precision. The most common one is FP16, which is like half precision. For serving use cases, 99% of the time, half precision is good enough where you don't need to worry about too much. So let's say you run it half precision, you're still talking about 900 gigabyte-ish GPU memory. So you have one of two options. One is you just wait until like either TPU memory gets bigger or GPU like GB200 comes out with bigger memory bandwidth, and you just have more memory to run this. So yeah, 2024 Llama comes out, and you'll be like, you know what? I'll wait till 2026.
But who knows? Maybe it'll come out and be bigger. You don't know.
Yeah. But the thing is, like Meta is probably thinking the same thing. When those bigger machines come out, they will train a bigger model, right? So I don't think it is completely unreasonable to think like by the end of this decade, we'll see foundational models crossing the threshold of 1 trillion parameter. Like I don't know exactly how many parameters we have on the Gemini models, but it is already probably closer to that number. But even in the open, we're probably going to get closer to 1 trillion parameter models. So again, now we have these big models. We have to run them somehow. And how do you go about doing that? So one of the ways people do that in VM world, well, not VM world is the name of actual conference. In the world of VMs, you would basically network connect multiple of these VMs together, and you'll manually manage all of this connection yourself. You'll basically spin up a head node, and they will talk to a bunch of worker nodes, and all of them are going to run the same application, and they will communicate, and they will do basically sharding of your model across both tensor. Like you will do tensor parallelism across the GPU and the pipeline parallelism to do the compute across multiple VMs. And
how does that even actually work? Are they like?
So
I'm guessing like some sort of gRPC socket connection, some sort of.
So it doesn't have to be gRPC per se. It could be pretty much any network, right? Like it is like you just basically need super fast network for each node to talk to each other. So it's like almost like a mesh.
Does it create like a mesh network? That was
you just have to create a mesh network. For one of the things these models are really good at, because these models are all they're doing, and this is almost insulting to the models because they do a lot more smart things, but generally what they're doing is this metric computation, right? Okay. And each of those computation just requires the previous result, doesn't require the whole matrix.
Okay, so it parallelizes really well.
Yeah, you could just parallelize them across. That's why GPUs is so good. GPUs are so good at doing this computation. You could just run them across all of them. And that's why TPUs are even better at doing this, because TPUs compute at the matrix level directly. In GPU, you have to basically serialize the matrix to do the computation. In TPU, you could just pass the entire matrix operation from the entrance and just collect the result on the other side. But anyway, we have this huge computation, and what you can do, you basically send the response, and as the computation is happening, the underlying server, like something like PyTorch, would then understand what the workers they have and where each of those data reside. And because they're all connected via mesh, they could then find out that this chunk of data resides in this VM. So send the data over to there and do the computation and come back with it.
Got it. Now, do these models come with like service discovery or anything like that, or is that part of the stuff that we're going to do?
No, that's part of these models. Any model that you see from Hugging Face or anywhere, this just wait. They're nothing about a model, right? The underlying engine like VLLM or TGI or PyTorch, whatever you're using to serve it, knows how to utilize these models to do the actual computation. Okay. There is this wonderful video series from 3 Blue 1 Brown that kind of covers how these models actually work. They break down the model architecture of GPT-3 or GPT-2. I don't know which one, but the one with like 175 million parameter or 1.75 billion. I don't know. It's like a fairly big model. But the idea is we're talking in hundreds of times bigger model now, but the underlying architecture is still basically the same. We're doing a bunch of matrix computation, and for generative models that generates text, you're basically saying, I have this text. Now look through your entire corpus. What is the most likely next bit of token that needs to be generated? And then pass the entire piece of token until now onto the system itself, like feed it itself, and see what the next token should be. And you keep doing that until you are done. Okay, so we have this big machine, and what we want to do is be able to shard the model into 2 VMs across all the GPUs to fit it. And in the world of Kubernetes, you could do a very similar thing to what you do in the VMs, right? You could just like spin up one deployment that is going to be the head node, and then spin up multiple other deployments that are going to be workers, and do that connection yourself. But what do you miss out on? The whole premise of Kubernetes that is self-healing. It understands when one of the workers go down. If you actually run 2 separate deployments and one of them fails, they're not really connected via any meaningful way. You know that they should be connected, but in the constructs of Kubernetes, nothing exists there that can say, okay, these 2 things should die and live at the same time.
Yeah. So like if you're doing a rolling update or like making any kind of change, there's no continuity between the 2. There's nothing. Yeah.
So if something fails, nothing in the Kubernetes controller world saying, okay, one part of this thing failed. So
keep the other thing alive. Yeah. Okay.
Right.
That makes sense.
Now, before I move any further, one of the things I do want to do is spin up a GPU node pool so that can take some time. And we're going to continue talking about what the solution to this problem is. And hopefully my YAML is my gcloud command is correct, which is fantastic.
So I actually want to pick at what you actually are doing here. So you're creating a 2.
So I'm gonna
so you have a cluster already?
So yeah, I created the cluster with this command, which is just create a cluster called LWS. In the project, which is Mofi Labs, the name is skillfully stolen from Kelsey Hightower's Hightower Labs. When I first joined Google, I saw like all his demos would be running on a project called Hightower Labs. And I thought, you know what? That's a good name. I'm gonna see.
Fair enough. I create and destroy projects at a whim.
So I do that. I like to do that, but GPUs, when you get them, you hoard them. So this project, I have a lot of GPU quota, which I would like to have.
I have other projects that I have CPU and IP quota on, but same
idea. So anyway, so I created this cluster, which we all saw a second ago. I'm not going to add a node pool this way.
Actually, we didn't see because you weren't sharing at the time, but we believe you.
So this is the cluster that, I already have created this cluster called LWS. It lives on US Central 1C.
Nice.
And this has, now it has more than 2 nodes because I'm spinning up 2 more, but it started with 2 nodes, 32 total CPU. Each of these node has 16 CPUs and 64 VRAM, 64 gigabytes of RAM. And this is the node currently. I'm spinning up more nodes for this particular cluster, which is being done using this command. So which is very similar to your traditional node pool create command. The only difference here is the machine type is going to be one of those A type machines, which has GPUs on them. So I'm doing the A3 high GPU 8G. The accelerator type here is NVIDIA H100 80 gigabyte. That is the latest GPU that is available. Next year, if we come back and do this again, we'll hopefully try to do this with the GB200 or something. And then we have the count of 8 because each of this node at max comes with 8 of these GPUs. I want the latest GPU version, driver version. So this is the NVIDIA GPU driver that is used for the container to talk to the underlying GPU. Placement type compact. It's not necessarily for this one because I'm on a single zone, but in GKE, one of the things you can do is say, when you are scheduling my nodes, try to make sure they're as close as possible physically, because when you are talking about GPUs that are talking among each other in like terabyte per second, the closer they are, the chances of being able to do that is better. Finally, I need to target what cluster I'm doing this on. So LWS is the same cluster that I created. And I only actually have Spot quota. Spot is preemptible VMs on GCP. I don't have on-demand quota for this. So it is possible after I run this for a couple of days, if a high demand, more on-demand workload comes in, my node will go away. But I'm doing this for just a few hours, so I don't expect it to.
You know what? It'll fail in the live stream just because
it probably will, and that is okay. This is again another proof that we are doing this live. If it does fail, I do have a video that we recorded and published a few weeks ago. I'll just
we'll just wait for it to come back. We'll be like, hey, give us another spot.
we'll just hang out. So we'll keep
It'll be
everybody hostage with us until it comes back. We'll just keep talking to them, because none of our viewers will actually live. I hope they'll stick it out with us until it works. Anyway, the cluster finally got created. Oh, that is actually quicker than I expected. That is good. But the GPUs to actually warm up and start being able to like be accessed takes a few seconds, which we can check with kube control get nodes. And we see that we have like 4 nodes now. 2 of them are our additional default pool and 2 from our GPU node pool. That's the name of the node pool I gave. So this is something I could have given. So this is the node pool. I'm going to describe one of those and see if it has GPU on it. It should. Kube control. Yes. The Mukamek. Thank you. I appreciate you. So kube control
as it takes.
Describe nodes and describe this node, and I'll get a bunch of text. I don't care about most of it. The only thing I do care about is this is not the part. This is allocated. So far I have allocated 0 GPU, which is true. But if I were to go up a little bit more, I should see that I have capacity of 8 NVIDIA 800 GPU. So
you can probably also see this in the Pantheon console, in the console.
Of course, you can see that in the console as well.
It's easier.
I am a terminal person, so I would do that in the terminal. But yeah, you can see that I have GPU attached to it. So this is a good sign that this is going to do what we need to do. So I think because this is a fairly big model, it's going to take a few seconds to download and run it. I'm going to quickly go over what this YAML file is going to do, and then, as almost like a recap, I'm going to talk about what we're doing here. Okay. Because I want to have let's get this running. So we're creating this thing called the leader worker set. Okay. So leader worker set is not a native Kubernetes API, so it doesn't exist in my cluster yet. Okay. I would have to install this construct called leader worker set in my cluster.
Have you done that already?
I have not done that. So we left that, and this is the doc. We can link it somewhere later. But I'm gonna install leader worker set into the cluster. And if you want to like find out about leader worker set, you can just go to leader worker set, and this would take you to this Kubernetes SIGs LWS webpage. And this is part of Kubernetes SIGs. It is maintained by Kubernetes maintainers. But the new goal of the Kubernetes project is to not add more things under the core API, just extend it out onto more things. So if I were to go down, there are some documents and other things here. The part I'm interested in is the installation. So this is like 2 patch release ahead of what the document says. Live dangerously. Let's do this one. Why not?
Oh.
So should be okay for the most part. So I'm going to install this version 042. It uses like it has the YAML file of all the things LWS needs to install. So if I scroll up the things, you would see some of the core ones are, it is installed a few CRD. It installed this role bindings to give those CRDs permission onto my cluster, some secret, the service, some deployment. So all of that fun stuff, some fun stuff. Validating hooks and all that fun stuff that it needs.
Pretty standard Kubernetes controller and operator.
Yeah, so we're basically adding one more controller into the mix, and then I could go see, how would I go see what have I installed? So I can, it adds a new namespace called LWS system. So if I were to go kube control get pods -n LWS.
Do you mean pods or pause?
Oh yeah, pods, or actually just PO is good enough. Anyway, so you see LWS controller manager. Each of them has like 2 containers in that pod, and both of them are up. This looks good. That's what we wanted. So LWS is up and running. And again, I could go back and see all these resources. But generally, basically, these are all the things LWS needs to operate in your cluster.
Cool.
So again, it needs certain role to be able to mutate certain resources that you're trying to deploy and things of that nature. And the other thing we're going to need, because we're going to deploy something that's a model, that the model data itself lives in Hugging Face, we're going to need to create a Hugging Face hub token. Yep. And I already created the Hugging Face hub token from Hugging Face, but I am just going to apply creating of the secret. So I'm going to just grab this, and I will read it out for a second. So kubectl will create secret generic. Name of the secret will be HF secret, which is the name I'm going to reference here.
Yep.
From literal HF API token, I have a variable Hugging Face API token.
We don't want to tell people what that is. That's fair enough.
Yes. So Hugging Face. Hugging Face is easiest way to explain Hugging Face would be Hugging Face is the
Hugging Face is Docker Hub, but for models.
Yeah, I was gonna say Git for models, but same idea. Yeah. So honestly,
and data sets and a few other things.
Yes. So if I go to Hugging, I don't have Hugging Face logged in onto this browser, but so Hugging Face has all these different models. If I look for Llama 3, just gonna find one of them, I guess. Meta Llama. I'm looking for Llama 3.1, I believe. Where is that? 7 collection.
How many llamas are there? Apparently a bunch. Cool.
Many. So the one we're looking for is, I think, Llama 3.1405B instruct. Instruct models are like basically fine-tuned for communication. And the other one. So one is for generation, one is for chat. So instructs are good for you ask a question, you get an answer back. And if you didn't have the instruct one, you would basically say Mark is A, and then the model will generate a bunch of other things after. So that's kind of the core difference. But we're going to be using this model that comes from Llama Meta. And this is a gated model. That means you have to sign some paperwork saying you're not going to use the model for X, Y, and Z use cases. There's a lot of things to read here. I obviously, as a personal intern, never read any of this. So if Meta put in a
not a lawyer, we are not a lawyer. This is not legal advice. Just making that very clear.
Yeah. So there is a bunch of things. I mean, ideally, this basically should just say things around like you cannot use this for like generating harm or hateful content and things of that nature. But if Meta wishes to say like, like we get your firstborn, I signed it already. It's too late for me. But generally, I don't.
Moving along from license discussions.
Yeah, licenses are tough. Let's not dwell too much into it.
Talk to your lawyers.
Talk to your lawyers or read it. It's not that long. You should be able to read it. I was just too lazy to do that. Anyway, I signed it. I agreed to it. Now I have in my account, I have access to this gated model. So what I can do, I can just go to my settings and create a new access token that has a read permission to any model that I have access to. So I have generated that token and brought it along on my terminal and created a variable called HF_token. So once I have done that, now I can create a Kubernetes secret with that token. So HF-secret has been created. So if any of my YAML in my namespace that the secret is in tries to reference it, it should be able to. That's pretty much all it means. Cool. Now let's break down literal worker set YAML really quick. I'm going to apply this first, and then we can talk about all the things, fun things that are going to happen. Keep control, apply -f, llama3.yaml. That's the entire YAML file I'm going to deploy. And I'm going to run a watch, keep control, get PO. So I can see the pods getting created. It's going to take a while. Again, first things first, I am creating now 2 pods instead of 1, mainly because I have 2 nodes that Mark was very perceptive to catch. I have 2 nodes, each with 8 H100 GPU. So I have a total of about 1200 something GPU memory.
Nice.
And because I'm running the model in FP16, which is half precision, I need roughly about 1,000 gigabyte of VRAM to load the model. I need a bit more to be able to do like a token, like input token has some GPU memory requirement. So in total, I'm basically about 80% utilization on my GPU memory that I have total. Okay. Now I have 2 of these pods that are spinning up. Underneath, they're going to be creating a bunch of other things, but that's the basic idea. Now you can think of each of those pods taking up a whole VM.
Yep.
Okay. Because again, these are like really big processes that are going to run. They're going to take up the entire VM. Now, if you go back to the beginning when you were talking about initially, was that I want to run a really big model. Then I have to create this one node as a head and another node as a worker.
Yep.
This is the same exact mechanism, but being done through a single unit of Kubernetes object.
And actually, if you kubectl get PO dash what is it wide, we should be able to see that they're on separate nodes.
Yeah. Yeah, 100%. So you could see that one of them is running on JT5X, one of them is running on H7WZ, the good old H7WZ. J. Yeah.
J.
Yeah. So
Don't disparage WJ like that.
no.
Exactly.
He's the seventh of the WJ name, so he's very
It's
famous.
important. It's important.
It's
I mean,
very
I did mess up your formatting there, but that's fine.
yeah. So they're running on two different VMs because again they cannot physically fit on the process requirement. If you go back and look at the resource they're asking for, this one
They're
is asking
chunky.
for is asking for a cool 1100 gigabyte of
Whew.
memory. This one is asking for like a small 125 CPU. These GPU nodes are fairly beefy. They're pretty big. They're asking for about 800 gigabytes of ephemeral storage to be able to download the model data and store them in it.
Yeah.
But okay, let's talk about the YAML, and this is gonna hopefully run eventually. But let's talk about the YAML now. Leader worker set. We're gonna jump into like how the leader worker set is structured and all that fun stuff. But the main thing to look at, instead of having a spec for a pod, we have now multiple worker specs. So you have a leader worker template. And the thing leader worker set does, it wraps a bunch of the Kubernetes constructs like deployment, stateful set into a single unit where you have a single controller that makes sure everything underneath the umbrella of leader worker set is starting up and getting like scheduled and scaled at the same time. That's kind of like the whole goal of this API.
And if I'm like just looking at the name where it says leader worker set, I'm guessing that what's what I'm looking for? This actually does set up with like some kind of maybe leader election and like some sort of, it expects some sort of like controller or like a leader essentially.
So
and a series of workers underneath it. Is that accurate?
It doesn't actually do a leader election. You elect the leader yourself. You just choose one of the containers as the leader. I'm going to show you exactly what
show me how that works. Yeah. Okay. No, so I think we're saying sort of the same thing, but
we're saying the same thing, but it's not as like randomized, because the reason is when you have a workload that requires something to delegate work and something to pick up, you technically could not have done that with the same code.
Right.
There is a slightly different set of code. They both run the same container, but the commands sent to each are slightly different. So you could not run.
No. I wasn't saying it would pick out of the set. I'm just saying that there is this helps you set up an organizational hierarchy where you have something that's the leader per se and a set of worker nodes essentially probably from there on.
Yes, exactly. So you have a leader worker template. Inside, you're going to see something called a leader template. This is where you're going to define the pod in your group of pods that are going to be the leader. So the leader is going to have, from this point on, this is going to look very familiar to like traditional Kubernetes.
Can I bug one thing on this?
Yeah.
You have replicas above leader worker template.
Yes.
Is that how many leaders you would have?
It's how many groups of deployment you're going to have.
Wow.
I'll get to that. This is a good call. I'm going to get to that. It's going to make sense, hopefully. So leader worker template, I'm saying the size of 2. That means 2 pod together makes up 1 replica of this deployment.
Okay.
So in this case, when I did kube control get pods, you saw I had 2 pods that are spinning up.
Yes, one with the other.
Those 2 together makes up 1 copy. This is kind of trippy.
Yep.
But it is not super different from saying like looking at a single pod that has multiple containers.
Yeah.
It's a similar analogy, but now my application is broken apart into multiple nodes. So these 2 pods together make up 1 copy of my application.
Okay.
So that's the replica 1. If I did replica 2, what would happen is I would have 2 sets of 2 pod that would spin up on 4 nodes.
Okay.
Yeah.
Got it. Okay, I got it. Yeah, so because you're defining like this is a group that's going to work together, and maybe I need multiple of those groups. That's fine. It's very much the replicas is like the deployment of pods. You're actually doing the deployment of workers or worker groups.
So in the world of leader worker set, the maintainers like to call this super pods, which is basically multiple pods being a single unit of work. Anyway, I have a leader container where I'm defining certain things like array cluster size, which is going to be in this case 2. I have a 2 node array cluster. The leader itself also is part of the worker. Like it does the leader work plus the worker work. Hugging Face Hub token that requires to download the stuff. And here is basically the magic sauce where I am running using VLLM underneath with Ray. And it is creating an array cluster of size 2. And then it's going to run some Python code of VLLM, which is going to set up a port, which is going to get the model, which is the same model that we looked at, a Meta Llama 3.1 405 beanstalk. And then these are the two numbers that are interesting,
Cool.
probably to people that are doing AML stuff. So tensor parallel and pipeline parallel. Now I'm going to try to explain this badly because I understand this badly, but I'm going to try anyway.
Okay.
So tensor parallelism is when your model is too big to fit on a single, sorry, which one is the, all right, pipeline parallel, where your model is too big to fit on a single machine. So you have to shard it into two in this case. Tensor parallel is a single layer in your model is too big to fit on a single GPU.
Okay.
So I have to basically break my, so because I have,
you're kind of like giving it a hint. You're like saying, hey, like you're going to be too big to fit on this machine. So you need to know that you're going to split up.
Right. So if I did not split it, what would basically happen is PyTorch by default would try to load up the entire thing. Again, VLLM, TGI, pretty much all of them underneath uses PyTorch. So they're just like wrapping PyTorch in interesting and clever ways. But PyTorch would then try to load the entire model into a single GPU with 80 gigabyte of memory. And then it will start working. And then halfway through, it will basically just out of memory and it will fail. In this case, you're just telling it from beforehand, you're going to chunk this model into 16 pieces.
Go. Yeah.
Right. So 2 of them are going to be just like model weight itself. And the other 8 is going to be model layer. You're going to break down the layer into 8 pieces so that you don't get out of memory.
Okay.
So once we do that in the leader, then we move down, and then there's all the stuff for the leader that is fun, and then we move to the worker template. In this example, because the leader is also a worker, I only need 1 worker. If I were to try to load this model into full precision, I would basically need 3 worker.
Ooh, I have another interesting question for you as well.
Yeah.
Because you had the images you're using. Where do those come from?
So these images are actually provided by the GKE team. They come from Vertex AI. And in the documentation, this actually lists you can use this image. There's also instruction on how to build your own.
Got it.
So let's just let's do this. I'm gonna grab the link to this doc. Okay, I'm gonna grab the link to this doc and drop it in our chat. I think that should go everywhere. Does it go everywhere?
It goes.
You tell me. All right, it's going places. Cool. Yeah. So that's the kind of the instruction that we published a few weeks ago, and then that kind of walks you through all the steps. The step
so those images that we saw before, like basically they're like, hey, here's a nice standard way to deploy a model of some kind.
So this image basically has the VLLM server like baked into it.
Got it. And VLLM, for people who don't know, is a bit of software that lets you run models, essentially.
Yeah. So VLLM is so it's similar to if you're familiar with the Hugging Face ecosystem, there's going to be TGI that you could have used. VLLM has a really close tie with the Ray team with Anyscale. Okay. So the support for Ray plus VLLM is very good right now.
Got it.
So you could do that. There is also instruction in this doc if you wanted to build this image out yourself. So you could actually build. So this image has both VLLM plus some of the other dependency you need. You can go look at the Docker file yourself if you are so inclined. Okay. So we have done that. Okay, I don't know what that is. I don't care. And in the worker, you basically, instead of running the leader, you run the Ray init with the command worker. Target the address, which is the LWS leader address, which is passed to the model via some environment variable. Or
where is that? That's the bit I'm really curious about, actually.
Yeah. So that one is not necessarily, you don't have to do that manually. I think that gets injected automatically.
Where does that come from? Well, it has to come from somewhere.
I think that is part of like the leader worker set, the controller itself that injects it into all the workers.
Well, hold on, go down. Go down. Let's have a look.
Yeah, LWS leader address. I think that's just get injected. That's only once here. Yeah, that is part of the leader worker set controller.
It's like something it does for you.
Yeah, that's the whole concept of leader worker set, is that I'm gonna have like leaders and the people are gonna need my address. So I'm gonna just do that.
I'm so looking for documentation on this, but I will.
Yeah, we can. I mean, you could go find it. Let's go.
I can do that in the background while you're doing other things if you wish.
Well, I mean, I have not much better things to do. Yeah, here you go. Add leader address.
So that is in a pull request. That is not in documentation.
Well, it's not. I don't know. Yeah, that was an issue, and someone closed it because that got completed there. That's how you find things, Mark. You've been in a
Yes,
long
that's
enough.
right. That's what.
So yeah, that's the code bit that does this. So we can go track this down if we want to. It is adding where is it adding? Okay, added run variable if not exist. It's just add LWS variable.
It just adds it. We'll see it. And actually, if we probably go look at the pod for
Yeah.
the worker, we
can
will
just
see
reprint them.
that as part of the spec on the container, as part of the information that is there.
Yeah, we could definitely do that. But just the sources, trust me, it does this. Okay.
We did get a question in chat. I think we sort of talked about this before, but we can go over it again. Love to know what role Hugging Face plays in all of this. Hugging Face is where we pull the models down. So from Llama, that's where we're going to actually like yoink it, essentially.
Yeah. So there is multiple ways you could do this. The model can also be grabbed from like Model Garden. You could grab the model from. You could download it from, I think, Meta directly. They have probably some repository they're like hosting the model in. I don't know. You could, once you have it downloaded once, you could just load it up on GCS bucket or your USB key or somewhere that you can get the model back out from. But in this case, Hugging Face is just being the repository for. It's the same idea. Your code, you could just move your code around in a USB key all you want. But if you want to get the collaboration back and forth and have some sort of lineage and see who downloaded when, all of that stuff, having a repository is useful. So you could do that via Model Garden from like Google Cloud, or Hugging Face is kind of like where the community has. Kaggle also, I think, has Llama 3 models. You can also get the model from Kaggle.
Interesting. Okay.
So yeah, so it's just the place where the model weights reside right now. All right, so a bunch of things are happening. I will just like do another quick look into seeing if we get to see any of the logs that are coming out of here. You could also obviously see the logs on the logging and GCP, but again, terminal person, I'm going to.
We have one running. Okay. So we have one ready at least.
Ready and not running is they're both running. They're just not ready. Ready basically means everything is ready to do things.
Yep.
So keep control logs -f. I'm gonna just log this one. So running. So the race has started. So I think the other process is just downloading the model weights, which is gonna take forever. So let's just like do that. Keep control logs -f, and this one is just gonna be VLLM 0. Yeah. So it's just downloading model weights. It's a lot of model.
Big.
It's pretty big. It's like a few hundred gigabyte. So it's gonna go and download that. So let's move on and talk about some of the other fun stuff that are going to happen here. After all of that is done, we're gonna set up something called a service. Now, again, in a regular Kubernetes world, your deployment has like one or many pod, but each of the pod have like a service address. So when you have a service in Kubernetes, when a request comes, it gets round robin into any of the pods under the deployment. Right?
Got it.
Which is business as usual. In this case, we don't want that. We don't want each of the pod to service anything. We only want the leader pod to take the request.
Right. Makes sense.
So when you are targeting the pod, you are not actually targeting the whole thing. You're basically just looking at with the selector, whichever has the role leader.
That makes sense. So actually, did you specify role leader or?
Yeah, it is defined right about here.
Got it. But the I'm guessing the leader worker set did the other label, which we also saw as well.
Yes. So this is the one that is coming from, like, this is literally the name of the leader worker set. That's the auto label that comes from this.
Yeah. Got it.
So this is also like defined by us. We could have changed it if we wanted to. But this is a
makes sense.
Automatic, like a label that gets added by the Kubernetes controller to any object that's created. You could just do it /name.
Yeah.
So you're going to find the selector of the leader worker set named VLLM, and then we're going to do the label of role leader, and that's where we want to send all our traffic to.
Cool.
We could do now the couple of other things that got created as part of this is keep control get stay STS. Is that the one? Yeah. We're going to see that all of these pods, they actually don't get created as deployment. They actually get created at stateful set. And the reason they're stateful.
Oh, fascinating. I actually would have thought they would have managed the whole thing, but clearly I'm wrong.
Nope. So the reason they're stateful sets is because we need to know if something actually does go down, we need to bring them up exactly as it were. Because deployment pods under deployment gets a random name assigned to them. We need to be able to address them directly because not everything gets a service IP.
Okay.
So stateful set makes sure that if, let's say, VLLM-0 goes down, it's going to actually come back up as VLLM-0 again.
Okay.
So that we could target it directly because we don't have to assign services to everything. That's going to just make it hard. So if I were to do kube control get service, you would see that I have this VLLM leader service. So VLLM leader is the thing that we're going to.
That was our service that we created.
The one we created.
The VLLM services system, I'm guessing, is probably something that
that's internally for things to communicate with each other within the thing. So while this is happening, it's going to take a few more minutes. So
I'll ask another interesting question then, maybe, which is that I noticed that, and maybe you don't know why, but I'll ask the question anyway. So we saw before that there was the LWS leader IP that we passed as an environment variable. Is that pointing at the service, or is that looking at, like, is there a service in front of the leader, which is what I would have thought would happen? So, or is it actually going directly to a pod?
So let's get to that. So this is the conceptual view of the structure. So you have the CRD, which is the LWS, which has everything underneath.
Beautiful.
At the very top level, we have a stateful set that actually keeps the state of all the different worker groups.
Yep.
Okay. And then you have this group 0, group 1. Each of this gray dotted line is a replica. So in this example, I have this pod, which is the leader of this group.
Yep.
And then underneath, there's another stateful set that keeps track of all the different workers.
Yep.
So in our example, what we have, and I don't know if the mouse you can probably see.
I can see it a little bit.
Leader worker set, CRD, that got created. One stateful set for the entire workload. And then one pod that is the leader pod. And then a second stateful set for all the workers. And underneath, one worker. So our line looks very lean like this. This is what we have in this setup.
But you could have multiples, is what you're saying.
But you always have one stateful set for the leader.
Got it.
And then you can have multiple of inside. You always have one here, one leader per worker group. And then underneath, you can have as many workers as you need to.
Got it.
Yeah.
Got it.
So the IP is going to be of this stateful set because this stateful set knows about this pod and every worker needs to know this pod.
Oh, okay. So you're not going to end up with a service, and I can't draw. I swear there was a thing in here that actually let us draw. But anyway,
probably
there used to be. But if I'm looking at group 0, for example, the pods that are at the bottom, they need to know to talk to specifically that stateful set that they're in group 0. They can't. So you could potentially have a service per group, but maybe that's overkill.
No, I think
so that they know where to.
You're going to have a service that basically round robins to these pods. You're not going to have separate service. For each of
okay. Yeah. No, I'm thinking about how the groups communicate up into the stateful set that is their leader.
So each group, this group only cares about this pod.
And would there only be one leader at a time? Like, would you have to? You have to specify? Hey, there's only one pod who's a leader.
Well, for each of the super pod group, there's only one leader.
There's only one leader. Okay, so you couldn't do like, hey, I'm going to run 3 pods as a leader, do leader election, and the one that's elected is going to stay there. And if one of them dies, then it can flip over. They don't do anything like that.
The thing is, each of the leader also need to have do work. So if you had 3 redundancy and one of them went down, your work would stop regardless.
Got it.
So this is
because the other ones wouldn't know. Yeah. Okay.
Yeah,
I get you.
Each of them has very expensive GPUs. If you wanted to have redundancy, I think the cost value prop of that is not.
Yeah, it doesn't make any sense. Yeah, I get that. That makes a lot of sense.
Yeah. So you have that, and then this is the structure we're looking at. And if we try to map that back again onto our YAML, we start again with the service being the service of the leader pod.
Oh.
And then you have the definition of the worker. So we have only one worker in this case. So that is behind one stateful set. And then you have the leader, which is the entire, all of the work groups, all of these replicas is behind another stateful set.
Got it.
So that's kind of the whole setup there. Let's take a look if we got this ready. Okay, it's still doing things. Again, it's still downloading.
20 minutes later.
let's
It's
so
fine.
yeah, it takes time, like good stuff takes time for sure. I'm gonna go back onto, so if you had the
Whoa.
chance to, Abdullah, one of our the maintainers of Leader Worker Set, and Rupeng from the engineering team actually gave a talk in KubeCon
Beautiful.
just this past week.
Yep.
I think the video of that should be out already, but the topic of the talk was Leader Worker Set for distributed inference. So that's basically what we're trying to do here as well. And this actually talks about exactly what he talked about, but in a bit more nicer diagram, I guess. The idea is when you have a model that's like 70 billion parameter, 100 billion parameter that can fit on a single machine, you just fit on a single machine. You just do that. The moment you have to go across multiple nodes, that's when the whole trouble starts. You have to do sensor parallelism, you have to do pipeline parallelism just to be able to fit the dang thing into your machines. So this is what we're doing here, right? So what the team has worked on is the new API named Leader Worker Set. It uses a bunch of things underneath the image we just looked at. There's like a bunch of this description here, how they actually work. Not super important, but the idea is we have a new CRD that we're going to create. That's going to be all YAML. Underneath is going to create a bunch of Kubernetes level resources on our behalf instead of us having to manually create those. So all of that will happen. And once it does, now the Leader Worker Set actually can follow your HPA. So you could set up the entire Leader Worker Set to scale up and down based on HPA metrics. Because again, we're treating the entire LWS as a single unit of deployment, if you want to call that. And you could look at HPA metrics of like usage, or you could plug in external metrics from CADA or something that says, okay, I have like an external queue that is seeing how many requests are coming in. I need to start scaling these things up. Couple of the other things just to say, because we saw how long it took for our node to start up, and it's taking how long our pod taking to start up. There are a few things we could do to make this process much faster. Number one, every time a new replica comes up, we have to first wait for the node to show up with GPU. And then we have to wait for the model to download, right?
Yeah, I was going to ask
the
that
node
question.
To show up part, there is very little we could do. Node has to be there for us to do anything. One thing we could do, which is just have a bunch of nodes sitting around for a workload to come in. But that's the huge waste. If I have a node already, why not just have multiple replica always running?
Why work in the cloud?
Yeah, right. We want to auto scale. So that part, there are some things we could do to like make the process a little bit faster, but we are working on that. You don't have to worry about that.
That's an our problem rather than a you problem.
Yeah. The model downloading part that we can improve significantly is in multiple ways. One, if you know exactly what model you're going to deploy, we could just package the whole thing into your image. So your image gets much bigger, but then we have a second problem is that now the image takes forever to download, right? We'll come back to that problem in a second.
Can we image stream? Oh, I interrupted.
I don't know. The image stream is a good idea, but even with image stream, for a model, image stream actually does not work because image streaming, for a model, you need the whole wait regardless. Even if you stream, you have to wait for the stream to finish. But the other part is like I could also like put the entire model on something like GCS bucket and do a GCS fuse to mount it onto my container. That way I don't have to copy the entire thing. So that is one way to speed it up. And the big image problem can be solved with secondary boot disk. So on GKE, we have a concept called secondary boot disk. You can attach a secondary disk onto your node at runtime, and that disk can be replicated. If you preload or one-time run it and load that image onto the secondary boot disk, any new node that comes up will just have that image already copied onto the boot disk. So you don't have to download the image back out from like Artifact Registry or like a Docker Hub or whatever. You just have the image on the node already because it's a secondary boot disk.
I should read this. This is useful.
This is great. Yeah, I'm a big fan. Abdel and I are actually talking about creating like a whole small series about speeding up, setting up inference servers. So if you just like wait anywhere between 1 week to 1 year, we'll have all of those public.
Definitely in a time period that is in the future.
No, we do plan to get this done sooner than later because a lot of our customers and folks are doing very similar things right now, like having very big images. And this kind of like is so funny because like back in 2017, 2018, when I first started getting into the container space, right? Like there was such a big push of like build smaller container images, have them like very small so that it starts up faster. And like it took us probably 10 years to get people to agree that, okay, we're going to build smaller container images. Like I still in the wild sometimes see like full Ubuntu distro from the base image and build everything on top. But for the most case, people are using like distroless, people are using Slim, Alpine. But then
sometimes you just gotta go big. Like it's
but
the thing that happens.
like, yeah, along comes like this giant of like this giant images like VLLM or TGI images. At the minimum, they're like 5 GB big. If you put in the whole model, you're talking like 200 GB of image size, right? So they're just big. So we could do that to speed up the startup time significantly. That could be like a really interesting way to make that process faster. You still have the challenge of loading all the weights copied into the GPU. So that will still need to happen, even if the weight is there. But if you don't have to download anything, that process can be faster. You're talking, instead of 20 minutes, you're talking like a couple of minutes. So in the grand scheme of things, when you're trying to, let's say you are scaling this based on some HPA metrics that you have a lot of people in the queue, the reconciliation time probably is going to be in minutes, not seconds. Again, technology is like catching up, I guess. Like it's going to slowly get better, but I still don't see how we can get like in few second time to get a model fully loaded onto a GPU. There are some things people are talking about like pre-warm GPU, because like if all you do ever is that load this exact model onto the GPU, but the pre-warm GPU then is going to come at a different type of cost because those GPU are getting held for you. So that's going to be some ways we can speed these things up quite a bit. So this is the other thing about LWS. Now the idea is, in a training scenario, you could do things like checkpointing to say if something fails in my cycle, I could scale this back up or like start from a set point. For inferencing, that probably does not make as much sense. So the general rule of thumb has been, if something fails, just destroy and restart. So in your worker group, if something fails, your idea basically is to just tear everything
take
down,
the whole thing out.
Back up.
Yeah.
So LWS, because it's a single unit of operation, if anything from leader to the worker, anything fails, it can just spin up a whole new and tear down the old one.
Makes sense.
It makes it super simple from operation side of things, that you are no longer having to think about nodes and VMs. You're just thinking of what does for your superpod to run.
Makes sense.
Yeah, so the next type of stuff that is going to be interesting is going to be topology aware scheduling. And the idea is, if your topology demands a certain set of scheduling, Kubernetes with the new set of scheduling mechanism will be able to schedule your nodes in the certain place. I have not read too much into it. I just like very tertiary reading on it. So in the future, we'll probably come back and talk about exactly how this works. But the idea is, when you're scheduling this workload, there is certain order of operation you need to have, because you have a bunch of these nodes and you are starting the leader and worker, and some smarts are being added to the scheduling so that you do it in a certain order.
Okay.
Okay, so you could do things like co-location. Where do you want them? Exactly what order? So you have a new thing added to the YAML, which is topology key. So you could say exactly what topology there should be part of. Again, we'll come back probably in the future and talk.
It looks okay. Yeah, there's okay.
But the key idea is like, make sure that nothing sneaks into that same node pool. All of the pod that should be scheduled gets part of the same node pool.
Which sounds very similar to what we can do already with pods and other things, but
yeah,
just tied into the leader worker set stuff.
And this is a little bit higher level, so that you could do like a one key, because otherwise you have to do like take this and don't take this. Here you're basically just saying just everything gets under this key. I guess this is going to be a little bit easier cognitively to think about what you're doing, rather than having to
it's providing keys so that you can group things as you want to, that may have been harder otherwise.
Yeah, for sure. Rolling update, same idea. When you're doing updates, each group will be shut down at the same time and upgraded at the same time, which you want in a thing that are working together.
Nice.
Reconciler, again, every Kubernetes reconciler looks kind of complex like this, but all you have to understand is the controller of LWS is constantly listening for the state. If something is not good, it's gonna like do something and fix it, and it's gonna keep going to listening to it again. There is a bunch of things happening inside because it's using a stateful set. We can mostly take advantage of existing mechanism in Kubernetes and not having to reinvent a lot of the how do I keep state of a group of things. So they're mostly leveraging the stateful sets mechanism already that keeps a hash of the
That's
pod
handy.
and just like does all
Yep.
the fun stuff. Yeah, so multi-node inferencing, same literally what we're doing right now. So you have a VLLM server and worker, and you have 2 node pools, and they're just like doing this. And at the end of it, we have a service that should be able to be ready and serve the request. And hopefully I have talked enough where this has caught up. It has not.
Ah!
Which is unfortunate, but it will. Let's look at the logs if
I was
something
gonna say,
fails.
let's
I
have a look
don't
at
think
logs.
so.
Yeah, it's going.
So this one is not the one. I want this one.
You want that one, yeah.
Okay, so this is still look like doing the
It needs like a good little percentage calculator thing.
It is, yeah. But
Like
that's the only
every-
thing left to do. Honestly, it's just gonna go and I think there is until it does it, it doesn't print the log.
Yeah, it just sits.
It just sits, so it is going to.
What was I
Yeah,
gonna...
that was pretty much it. So once this is gonna be done, we will jump into just like sending a request to this model. A few weeks ago, one of the essays and myself, we actually made this into a video. So if I want to quickly jump after I see this ad, I'm gonna.
After you see this ad, yeah.
All right, thank you. That is me. That's my background. That's so basically once this is done, this is what it's supposed to look like. What is supposed to look like? Let's move on to it. Here you go. So we have this VLLM leader. Okay, so once everything is running, it's gonna basically just say VLLM-0 is running instead of like
that is
0
tiny.
1.
There is no way anyone can see that.
Oh, okay. Let's make this bigger.
That's better.
Yeah, okay. I can probably also bump up the quality so that it's not. There you go. That's a little bit better.
Nice.
I can't zoom in anymore. Should I be able to zoom in? That's interesting.
Think so.
All right, I can. It's fine. So you have this VLLM-0 that is ready, and then what I would basically go and do is look at my VLLM leader, set up a port forwarding to that, and just from that point on, it's just business as usual. I'm just sending your traditional VLLM JSON request.
Go guess what the inputs and parameters are, and then
yeah. So I'm just like, again, this is the instruct model. They do both chat and completion.
Yep.
We just sent back like San Francisco is A, and then we're gonna, after a few seconds, we're gonna get just JSON blob coming back from the model that says top destination for foodies and with X, Y, and Z. So yeah. So again, I'm happy to chat around other things if you had any questions or people had any questions.
Very curious to see if it's come up yet.
I would like to know too. This is making me look bad.
I blame you entirely.
In front of all my new cool friends. We're just gonna have that running here. But it's also possible that like the new .2 patch version completely broke everything.
Did it break everything? That would be unfortunate, but I've been there, so that's fair enough. Trying to see. Do you have that full YAML file available anywhere on the internet?
Oh yeah, that's, again, part of the doc. All part of the doc, all part of the plan.
Beautiful.
This is right here. All of that.
And that's that would be this one here that you linked.
Yeah, it's part of the other doc that it's part of the multi-host GPU link that we had shared already. Yep.
Yeah, I can't click it because I'm here.
Yeah. So if you basically, so this is the bad part because we publish so much stuff there. The easiest way to get to it, if you just do GKE LLM serving, is gonna take you to like one of those pages. They're all next to each other. And then you want to go to the one multi-host GPUs. That's the.
Oh, I see it.
That's the easiest way to get to it. Again, not the best way to get to it, but the easiest for sure.
I think this is the one. Okay, yeah, serve an LLM with multiple GPUs. It's not serve an LLM
it's not
on multi-host.
GPUs, multi-host GPUs.
Multi-host GPUs. There we go. That makes more sense. Okay.
Because
And that's
the
what
example, actually, this is a good call out as well. The example that we have for multiple GPUs, this still fits on a single node. We put like 4 GPUs together, but on the same node. But the difference here being we're actually putting that across multiple nodes. So that's being the main difference. And I think one other thing I was going to quickly call out is we talked about like multiple parallelism here. So pipeline and tensor parallelism. There's this article I just like randomly found on the internet that has actually quite a decent explanation of what that is in practice. So this is kind of basically the main definition of and difference between them, right? Pipeline parallelism is used when an entire model is too large to fit on a single device.
Yeah.
So the model is split into stages, and each stage executed on a different device, passing activations between neighboring stages when a boundary is reached during execution. So activation is just like the term that is in it's basically the matrix computation. It's called an activation once like some computation happens with the weight biases. And you just like pass them along. And the other one is the tensor parallelism, which is defined somewhere here. Yep. So if a single layer is too big to fit in a single replica, then you do tensor parallelism. You just basically break down a layer from GPU to GPU. So for Llama 3, 4, or 5 billion, there are layers within the model where each single layer might be bigger than 80 gigabyte.
Got it.
So, which is not great.
The other thing I'll ask you as well, because we were looking at the YAML file there for the VLLM YAML. Say I'm like, okay, cool, this is great. I don't want to use Llama. Maybe I want to use something else, or maybe I want to tune things in a different way. I see that it points out, this whole like workspace, VLLM examples, rayinit.sh. Like, how do I know what to push into that? Like, there's a bunch of arguments in there.
Oh yeah, so that code comes from the.
There's like 4 different things in there because you've got the rayinit. Then apparently you're also running this VLLM thing, and then like how
code. So if I were to go there, I would. Where is the examples at? Let's go find that. Docs maybe. Yeah, docs example VLLM GPU. That's where this one is. Oh, I think that's part of VLLM itself. So VLLM, GitHub. Let's go find it. VLLM project, maybe example.
That makes more sense. Examples. There's a rayinit file in there?
That's a good question. I just want to go see the Docker file. Probably says exactly where they copied it from. I saw it like a few weeks ago, but this is a good call out. So it's part of LWS. And VLLM, docs example, VLLM build, and this. So this, we have copied the code over into it. So that will probably point me towards exactly where that file came from. Okay, this example, VLLM build dockerfile.gpu.
Oh, there's your rayinit.
Yeah. So we're just like, so this is part of VLLM workspace rayinit. And this is the rayinit itself.
And it is...
It's pretty dense, but not that bad. You are just like, you have a bunch of ray commands in it.
So basically, okay, so I'm just building the layer of foundation here as I'm thinking through this. Understanding ray.
Mm-hmm.
Understanding our Docker file. Understanding VLLM.
Oh, yeah.
Then you're going to be able to work out what all your commands are.
You're close then.
Probably.
You're pretty close, right? So basically, so ray is pretty big. But again, one of the things I spoke to folks about, because like in running ray on Kubernetes, this is the manual way to run ray on Kubernetes. You're basically running ray in a container and running ray in a separate container and making them talk. The way we do run ray on Kubernetes is using kuberay, right?
Yeah.
But it's basically a matter of who reps who. So
because in this instance, we're not running kuberay. We're just running an instance of ray in a container.
Yeah. So, but the issue is, I don't think kuberay have an understanding of running leader worker set underneath it yet.
Yeah.
because Kubernetes can run Kubernetes pods, but not leader worker set. Again, they're like kind of separate things. In this case, leader worker set is more flexible for you to be able to run like Ray underneath, or the other way. Ray is more flexible to be able to run underneath something else.
Yep.
But leader worker set is not something you could run as a CLI to be able to run under Ray. So in this case, we're doing leader worker set that just wraps Ray as a container.
Got it.
So yeah, we're doing that one. And I read through this. It basically says like copy this into this file structure.
So it's pretty lightweight over the VLLM OpenAI image, essentially.
Yeah, basically this is just the VLLM image. We're just copying in one shell script that does some of the Ray stuff automatically on our behalf instead of us having to manually do some stuff. And this defines up like worker command and leader command. So if you put the worker, everything else underneath is just like the flags and things you would pass to the worker.
Got it.
And under the leader, everything else is passing to the leader. And I think all of that gets passed to the underlying Ray command itself. It's a pretty lightweight wrapper on the Ray command. But yeah, so still not ready. So I don't know if it's going to be or when, but I guess I'll report back if it ever starts.
That is that would probably also get into another interesting question, which actually we ran into in the last live stream. Is like, this is failing, for example, or maybe it's not failing. We don't know. How do we debug this stuff?
It's harder. So you could do kubectl events. Readiness. That's different because this has not started yet, so it's gonna continue failing. So the big errors on a workload like this that could happen is that I didn't get a GPU, so I would see my GPU count to be 0.
Yeah.
I didn't get a node, or the image could not be found, or image could not be downloaded, or did not have enough storage. All of that should like surface up in some sort of pod level failure.
Exactly.
But some of the Ray stuff that is problematic, where the pod itself is running because the pod itself is only running Ray.
Yeah.
And then Ray is failing, but that is not. It just keeps on retrying indefinitely and never actually calls out that it failed.
Yeah.
That might be something on the setup on the Ray side. Like at what point it should fail the process itself.
Verbose slugging or something like that is possible.
Yeah, you could on the Ray command. If you're running Ray through command line directly yourself, if you're running Ray as a job, that would actually surface up on the Ray cluster that the thing is running on. In this case, we're not setting up a Ray cluster. We're just basically running 2 separate Ray processes.
And when we say Ray cluster here, we don't necessarily mean a Kubernetes cluster. We mean the construct of a Ray cluster, which could run inside a pod, if I remember correctly.
Oh boy, yeah. That's a whole other kind of form. So this is not the Ray on GKE thing, but I think it is important to talk about this here. So Ray itself, it can be a scheduler because Ray has a concept of head nodes and worker nodes. And then all of that together runs in some resources, which happens to be what we call Ray cluster. So Ray cluster, for the most part, when you run Ray by yourself on VMs, what you do is you have a bunch of VMs that you want to work together. You set up a head or many heads, and you have a bunch of workers. The heads know and have control over the workers. And together, you can set up like a Ray dashboard and Ray cluster and scheduling mechanism. Now, when you bring Ray over to Kubernetes, running a scheduler and a scheduler is usually looked down upon. We don't condone that kind of behavior. But that doesn't stop people from trying to run Ray on Kubernetes. So you could run Ray on Kubernetes, but the compromise here is instead of running a full on Ray on Kubernetes, you basically create a new Ray cluster per Ray workload. So you still have the concept of Ray. It can auto scale up and down on the cluster level, but you just don't, basically you don't take over the entire Kubernetes cluster by running Ray. You run Ray as a workload. You consider each of the Kubernetes pods as like a VMs that the Ray has control over that can auto scale up and down. So it's still at times kind of weird to think about a scheduler and a scheduler, but for the most part, I think it is still like it does not break anything. It works pretty well. Abdel and I actually talked about Ray this KubeCon, and just like the introduction to Ray, where it comes from, what we're doing there. And that was like an interesting thing people talked about. Like, what does it even mean to run a cluster Kubernetes I thought was the cluster. What is happening? Right. So um, it for the most part it works. I think there are still work needs to be done in terms of the thing you said about surfacing the errors and issues properly, because there is like multiple layers, and sometimes you don't exactly
Really?
sometimes you do see an error, but you don't know exactly what caused it and
Where
which
or
layer
which
it failed
layer
on.
it came from? Yeah, exactly.
Yeah. And it's the same problem of if you're basically running a deployment on Kubernetes and it says the deployment failed, usually you don't have too many things to look at, because deployment failed, it is either the replication controller or
Yeah.
the pod. There's only like two things it could fail on. But now we are basically wrapping a pod in a stateful set in another stateful set in a controller called LWS,
Yep.
which itself underneath is running Ray. So at
And it's
least
much
we have
harder
5
to be
layers.
like, how do I run this on my machine? Like if you're running a web server or something, you're
You
like, oh, I
don't
can run this
for
locally and
this
have a
one.
look. And this just can't. Like it's
You
just not
just
possible.
do not do that.
Yeah.
It is not the most replicable set of things, but that's kind of the nature of the beast. We're running like some really, really big things. Like even in the world where you could locally test it, you name like 5 people that has over 1,000 gigabyte of VRAM available on their local machine. Like you just don't have that. I do however, have like a 3090 on my desktop.
Mhm.
But if I had another one of this, I could replicate some of this behavior by doing 2 pipeline parallelism on a much smaller model.
Yep.
And kind of like have leader workers that handle the 2 VM situation. But even then, both of those VM would be part of the same physical machine.
Yeah.
So I don't
So
even
you're in the
have
same
to
spot.
actually go to leader worker set for that. I could do a straight up deployment.
Yeah.
I could like create the situation by running 2 VM and each VM talking to one of the GPU only, and then running a leader worker set across VM 1 and 2.
Yep.
But I feel like setting up that scenario for testing is just going to be so much more work.
It's not worth the effort.
So this is the last check. If that doesn't work, I think I'll just call it. But you get the core idea how this is supposed to work.
Go on, check the logs. Check the logs, Alex. Check the logs. Go on.
Yeah, this is going to bother me. I'm going to. One last thing I can try to do as the last ditch effort is, it just started.
Hey! There we go. Just took a while.
Yeah, it took a while. So what happens is basically until literally entire time it would say nothing until it actually gets to download the stuff.
Yeah.
It will print all the download at the same time. Mainly because this is not like, if you did this in like something like a notebook, you would see that like a green line going up. But on a like a terminal on a container that is writing to a process does not have the graphical fidelity to write like a process progress bar, right? So
you can just push stuff to foreground. This is possible.
And but I feel like for VLLM wants to be user friendly for the people that is running it directly, not for people that are running any. I'm pretty sure you can pass it as a flag. I'm pretty sure you can pass it as a flag, but it did not bother because when it runs, it just runs. I don't have to worry about it.
Okay.
All right.
Okay.
Let's do the thing. Keep control. Get service. I'm gonna port forward the service.
Cool.
This service. So keep control. Port forward service / name of service, and I can just port forward the service. And one tip, if you did not know, if you just name one port, and this will basically do host and pod with the same name. You don't have to do colon if you have the same name on in and out. So I can just do this. So it's port forwarding to port 8080. And I'm going to basically go and copy one of the things. That's the command we had run in the past. I'm going to just do the same thing again. Okay, let's say you want to learn something different instead of this.
Pick a different city.
Yeah, okay. I mean, I'll just represent.
There you go.
The max token is set to pretty small. Again, this serving is going to be fairly slow because it has to do the computation across 2 nodes. But I could bump it up. Not super big, but I can bump it up to, I don't know, 28.
20.
Let's say.
Okay. It's a very.
I don't know, just number. 7 times 4. It just felt right. Okay. If that works, it's gonna take like 4 times longer. All right, it did it. Oh, one trick I learned. I could basically hold on. Let's see if it
Oh,
works.
pipe the output to JQ or something.
Yeah, but like I have to do a. Oh no, that's happening. Literally, my keyboard is not moving anymore. It's fine. I'm gonna just pipe
There we go.
it to J. Yeah. Okay, I'm gonna pipe it to JQ-R. If I could put in a -S in front of the after the curl, it would not have printed any of this. But we will have to see that now. One of the other ways you can improve this as well. Oh, here you go. Much nicer. New York is a city that never sleeps, and neither does its food scene. From
Oh, now I'm
classic New York
hungry.
style pizza to bagels, pastrami sandwiches, and you'll fill
Uh
in the rest. That's the 28 token. 28 token we reached. The other thing we
There we
could
go.
do, and I'm gonna not here. I'm gonna go to here. The other thing we can do is go over here, and if I were to go to, let's say, localhost 8080/docs, that would not. What did I do wrong?
Because it's your local host, not the local host on.
Oh, right.
You
My
need to.
God.
You need to. You
Yeah,
can,
web
yeah,
preview. Web preview. There you go. If I go to this, but instead of all this, I'm gonna say docs. This gives you a full like a open API thing. We could do the same thing here as well to chat completions here.
Hey, I want this on all models. This is good.
If it is using the VLLM and TGI, they're gonna have this.
Interesting.
Yeah. So
one of the things that's actually like made me climb walls is just not having an open API spec for basically a model, because it seems like that just seems like an easy win.
It's not there yet, but obviously it's getting there slowly but surely. So you can try it out and see what models you have in the thing. You see that the model you have is MetaLlama.
Yep.
3.1.
So this is served. This is served out of VLLM. Is that right?
Yeah. So VLLM. So if we
We'll
actually look at the exact command we are running out of, where did it go? What did I do here? Oh, here it is. Exact command we're running out of here, which would be
rain it, blah blah blah.
No, this is the worker. That's not the one. This right here. So we are running a OpenAI API server.
Right.
That's the entry point we are running.
Got it.
So this is fairly new. This is, I think, part of from VLLM 0.5. As before that, VLLM is to run like a different API server, which has limited amount of OpenAI, like OpenAPI implementation. But with the new one, it has a pretty nice. Like this is a fast API implementation of the whole thing. It's quite nice. I like it. So yeah, you can get like a version of things, like what version of things you're running. This is you can know that we're running VLLM 0.5.4 here. That's pretty great. And the completion would basically let you send information. So this is chat. Basically means you could send in turn order. You can send like previous messages as part of this message. So before, people used to do that by basically keeping track of the entire thing themselves. But now you could just do that as part of this. So you have chat completion, you have regular completion, which is just complete a piece of string, and you have embeddings. You could actually use this model to generate embeddings too.
Yeah.
Which is actually like such a nice side effect of these models, because every single of these models, to do the work they do, needs to generate embeddings anyway. So you're almost like getting a side effect benefit. Like, okay, the embedding you generate, just give it to me. I'm going to store this in a vector database, and I'm going to have
somewhere I can use it.
RAG doing things. So, well, I'm glad that I didn't have to like settle for just showing at TV. I think perseverance. That's the lesson here. Perseverance wins. You gotta sometimes go some back and forth. But yeah, so that's pretty much it. That's like serving really large models. Not everybody needs it. Almost nobody needs it, but the people that do need it are going to be very glad that this works. So yeah, you could also use the model to tokenize things. You could see exactly how this model tokenizes things. Actually, test it out. So I have to pass in what model it is, and let's get a prompt. Let's see how tokenizing works. New York is a city that never sleeps. I don't know what it would do.
Let's see what it does.
Oh yeah, that just generates some tokens from it. These are just like the Unicode value, I think.
Okay. I don't know what that means, but I believe you.
Yeah. half the time I don't know what I mean either, but here we are.
I think you understand what you mean more often than not.
Yeah, so we served a very large model. So we should
Cool.
all feel very proud, including myself, that we have
Well
done it.
done.
We
Well
all
done
have
indeed.
learned a bunch of
Yes.
things, hopefully. And leader worker said, of course, like again, when you are doing that for, as I said, very few people actually needs to do that themselves.
Yeah.
But when you are accessing these models being served across, if it is running on Kubernetes, leader worker set is going to be the way to do it in the going forward. Because without it, you have to basically build a bunch of tooling yourself to make sure that everything is coming up and down at the same time.
Beautiful.
So maintenance of that is absolute nightmare for us. Again, it took some time because we're downloading a very big model and took some time to load everything up. But from this point on, for any reason, if any of my pod goes down, like I can go just again, this is not gonna finish in time, but just to kind of prove the point, I could just like go out of my way and say keep control, get PO. If I basically just say keep control, delete PO, VLLM.
After all this time, you're going to take it down.
Oh yeah. So if I just delete this pod,
then all of it should go, right? Or all of it should get recreated.
It's just going to get recreated automatically. I don't have to do anything. And this could be because my node got busted or like we got like flooded in our data center and one of the VM went down. Any of these things does not matter. Like I don't have to worry about both of them. They're going to come back up. It's going to take some time, but I'm not worried that they're going to come back up. So that's the whole point of Kubernetes. Self-healing. Something goes back wrong and something comes back up.
Yep.
And for multi-host serving, that was not true until maybe like 6 months ago.
Yep.
With leader worker said now that's true as well.
Beautiful.
So if I do keep control, get PO again, and that's kind of the beauty of stateful set. Because it was a stateful set, the pod name stays the same. The new pod that comes up is the same. And as you see, both of them are 9 seconds old. So the whole setup got recreated.
Got it. That makes a lot of
I
sense.
think that's a good place to end the demo. I think.
Yeah, that seems pretty good. Anyone go like if you have any last minute questions, drop them in chat.
Yeah.
But that does seem like a pretty cool spot.
I
Before
can
we wrap
answer
up,
pretty much a lot of questions about Kubernetes, about board games, RPGs.
Blood on the Clock Tower. We can talk a lot about Blood. We can talk a lot about Blood on the Clock Tower.
We could talk about Blood on the Clock Tower. Actually, Mark can talk about Blood on the Clock Tower as well. We, it's kind of an aside. Mark got to play, I think, one of your first ever games last couple of weeks ago in a charity match.
It was my first time playing as a player and not storytelling, so not leading the game. So that was a lot of fun.
I would maybe not part of this live stream, but I would like to chat with you about that experience. That was I got to come back in the later half to spectate. It was fun.
Yeah, it was fun. We can talk about that.
Yeah.
So. All right. Looks like we're not getting any questions. So Mofi, I'm going to say thank you very much for joining us, and thank you very much for spending the time and showing us all some cool stuff and teaching me some cool shit too. So it was some good stuff too. So that'd be great. Awesome. All right. I'll see you all later. Thank you very much.